Quantum computing might be the most hyped technology of the 21st century. And with that hype comes a wave of misconceptions, exaggerations, and outright myths that have taken root in popular culture, in the media, and even in conversations among otherwise well-informed people. Some of these myths make quantum computing sound like magic. Others make it sound like an existential threat that is right around the corner. Almost none of them are accurate. So today we are going to do something that does not happen nearly enough in tech coverage. We are going to slow down, look at the most common myths about quantum computing, and replace them with what the science actually says. No sensationalism, no doomsday predictions, no breathless proclamations. Just honesty. Myth number 1. Quantum computers are just faster classical computers. This is probably the single most common misconception, and it is wrong in a fundamental way. A quantum computer is not a classical computer with a turbo button. It is a completely different kind of computing device, built on different physics, and designed to tackle different kinds of problems. For the tasks that classical computers already handle well, word processing, browsing the internet, running apps, playing video games, a quantum computer would actually perform worse, much worse. Quantum computers are not general-purpose speed machines. They are specialized tools that, for certain specific problem types, may offer an exponential advantage over classical approaches. The distinction between faster at everything and potentially better at a narrow class of problem is enormous, and collapsing that distinction does a real disservice to public understanding. Myth number 2. Quantum computers will make all encryption obsolete and are about to break the internet. This one contains a kernel of truth wrapped in a very large amount of premature alarm. It is true that a sufficiently powerful, fault-tolerant quantum computer running Shor's algorithm could theoretically break RSA encryption, which underpins much of today's internet security. That part is real, and it is a genuine concern that governments and security researchers take seriously. But the word sufficiently powerful is doing an enormous amount of work in that sentence. To break real-world RSA encryption, you would need millions of high-quality, error-corrected logical qubits working in concert. The most advanced quantum computers today have a few hundred noisy physical qubits, and the jump from where we are to where we would need to be is not incremental. It is many orders of magnitude. The cybersecurity community is not ignoring this. NIST, the National Institute of Standards and Technology, has already standardized post-quantum cryptographic algorithms designed to be resistant to quantum attacks. The transition is happening, but the threat is not imminent in the way many headlines suggest. Myth number 3. Quantum computers can solve any problem instantly. This one is pure fiction, and it stems from a misunderstanding of what superposition actually means. Yes, a qubit can exist in a superposition of 0 and 1. But this does not mean a quantum computer tries every possible answer simultaneously and just reads off the correct one. Quantum algorithms are subtle, mathematically intricate procedures that use interference and entanglement to gradually amplify the probability of finding the right answer. They require careful design for each specific type of problem, and for many categories of problems, no quantum speedup is known or is even believed to exist. Quantum computing is not a magic oracle. It is a different computational paradigm with its own deep mathematical theory, its own limitations, and its own unsolved problems. Myth number 4. Quantum computers already exist and are being used to solve major real-world problems. Companies like IBM, Google, IonQ, and others have built real quantum computers, and this is genuinely impressive. But the systems that exist today are what researchers call NISQ devices, noisy intermediate-scale quantum machines. They are real, they are operational, and they are valuable for research. But they are not yet solving problems that classical computers cannot also solve. The much-publicized claim by Google in 2019 that they had achieved quantum supremacy, demonstrating that their quantum processor performed a specific task faster than any classical computer could, was a genuine scientific milestone. But it involved a carefully constructed mathematical task with no practical application. IBM later argued that an optimized classical algorithm could perform the same task in far less time than originally estimated. Quantum computing is progressing. Practical quantum advantage for real-world problems has not yet been demonstrated. Myth number 5. Quantum computers work by trying every answer at the same time through parallel universes. This is a popular interpretation that some physicists do loosely invoke, but it is deeply misleading as an explanation of how quantum computers actually function. The many worlds interpretation of quantum mechanics is one of several competing interpretations, and it remains philosophically contested. Regardless of which interpretation of quantum mechanics you subscribe to, the practical operation of a quantum computer is fully described by the mathematics of quantum theory, wave functions, operators, probability amplitudes, without needing to invoke parallel universes. Explaining quantum computing as trying all answers at once across multiple universes might sound exciting, but it obscures the actual mechanism and gives people a fundamentally incorrect mental model. Myth number 6. We are just a few years away from a fully functional quantum computer that will change everything. Timelines in quantum computing have a long history of being optimistic. The field has made remarkable progress over the past 2 decades, and the pace of development has genuinely accelerated. But building a large-scale, fault-tolerant quantum computer, one that can run deep quantum circuits with millions of error-corrected logical qubits, remains one of the hardest engineering problems ever attempted. Experts disagree significantly on timelines. Some believe a fault-tolerant machine could arrive within 10 to 15 years. Others think it could take much longer. The honest answer is that nobody knows for certain. Progress is real and meaningful, but declarations that the quantum revolution is just around the corner should always be treated with a healthy degree of skepticism. None of this is meant to diminish the genuine wonder and importance of quantum computing. The science is real and it is profound. The potential applications in drug discovery, in material science, in optimization, in our fundamental understanding of chemistry and physics are legitimately extraordinary. But the gap between what quantum computers might one day do and what they can do right now is large, and filling it is the work of thousands of scientists and engineers who are making steady, difficult, hard-won progress. Separating the myths from the reality is not pessimism. It is the only honest way to appreciate how remarkable this field truly is.